So, thank you very much for coming to our talk. So we will be talking, as I said, about cache information when you are using Windows Hello for Business and Try ID. So first of all, who are we? So we are 3 security researchers from Synactive. So Théo and I are from the penetration test team, and Rémi is from the reverse engineering team. So just a quick word about Synactive. I won't be talking too long about that. So we are an offensive security company based in France. We are almost 200 security experts focusing on penetration tests, red teaming, reverse engineering, vulnerability research, development, incident response, everything that a security company can do. And we also have a conference in Paris, Hexacon, so if you do nothing in October. Just a quick agenda, so we'll be just focusing on how we came up with this research, have a lot of definition about Windows Hello for Business and Try ID. We will be talking about the cache data formats, what is possible to do for offline authentication, a quick demo of our tool sets, and a word on DP API, because it's quite important on the new cache information. So, to start, all this research started during a penetration test. We had to perform an audit on our workstation. The client wanted to know what's possible to do if we stole a laptop from us. So the workstation was encrypted, BitLocker and TPM, but no PIN code was required to boot. So we just sniff in the BitLocker key through the bus, decrypt the disk, and we saw that the computer was in a fully Try ID environment with Windows Hello for Business, and there was no MS cache store on the computer. So we know that it was possible to access to the domain even when we weren't connected to the internet. So we know that there is some cache data somewhere. So we decided to have a look at it. So just a few definitions. What is Windows Hello for Business? It's different from Windows Hello. Windows Hello is just a way to authenticate on your computer. It's pretty straightforward, using a PIN or biometric gesture or everything to log in on your computer, on your personal computer. And it's basically just a password when you are using Windows Hello. It's just an easier way to connect to your laptop and not to remember a password. So you can use special thing, faces, fingerprints, PIN, you can use a physical security key. And basically, when you're using this, you can retrieve the password of the user, since if you're using only Windows Hello, the SAM IVE is no longer used, but due to DP API, you will have to have the password of the user somewhere. In fact, you only have to have the SHA-1 of the password, but Microsoft stored the clear text password somewhere. So this research was already done by Tish the Nuts, and that's a lot of crypto implied. I won't be going too much into detail here because we are going to do the same for the Windows Hello for Business. So if you want to have a look, just go there. What you have to remember, if you have a PIN, you can, at the end, decrypt the password of the users. So we found this research and we say, okay, what if when Windows Hello for Business, can we have access to the clear text password somewhere? That was really nice to be sure, but Windows Hello for Business is not the same as Windows Hello. It's not password-based. It's some kind of asymmetrical authentication. So the PIN that you use will be used as the public and private key. So when you're joining a domain, you have to reboot the computer, and then you will be able to join Windows Hello for Business. You create a PIN, and the PIN basically creates you a private key and a public key, and the PIN is an entropy to protect the private key. So it won't be possible to retrieve the password that way, but we found that if you are using a TPM, the PIN is used to access the private key, and the private key is stored on the TPM. But if you're not using a TPM, the same process applies, but everything line on the local drive. So could be interesting because we know that every workstation now use a TPM, but we know that a lot of servers, a lot of virtual computer does not use TPM. So could be interesting for at least a few years again before everything is virtualized. So we decided to have a look. So just to remember, how does it work when you have an authentication with Windows Hello for Business and you have access online? So WinLogon just asks you for the credentials, so you're using your PIN, your faces, everything. You just send it to the Cloud API providers, and the Cloud API provider just requests a nonce to Entra ID, and this nonce is signed with the private key that we said was used by Windows Hello for Business. So once you sign the nonce, you send it back to Entra ID. Entra ID validates that you have access to the private key. If you have access to the private key, it means that you have the PIN. They say, OK, validate it, and it sends you a PRT, which is equivalent to your access to the Entra ID tenant. With the private key, with the PRT, you decrypt the session key, you import the session key in the TPM, your authentication is successful. Okay, so there is a lot of definition. I think most of you are pretty familiar with it, but I will go a little bit with them. What is interesting is that if you have access to the PRT, you basically have access to the Entra ID at the users. It can be seen at the TGT on Microsoft Active Directory. What you have to understand is if you have access to the PRT, you will be able to do as much as everything you can with it since it's valid for 14 days. DJ here did a lot of research on that, and you can use that. So it's pretty nice to have access to the PRT. Okay, so another part of the process is the cloud authentication provider, the cloud API provider. It's basically just the provider that is using LSAS to authenticate you to the Entra ID. So it's basically all the functions are in cloudapi.dll. It's live in lsas.exe process memory, and it used authenticated you to the Entra ID. So it implements the sake package function table structures as every credential providers, and the function responsible for the authentication is LSA AP logon user x2. It's not documented by Microsoft, as a lot of things done by Microsoft, but you can find a lot of documentation in LSA Whisperer wikis, since it's just a credential provider. Yeah, sorry, I was just looking at the clock. So what if Entra ID cannot be reached? Then the user is still able to perform local authentication, and it's based on the cache file. So when you are using the LSI ape logon user x2, it's executed with the cache interactive instead of the remote interactive. So we know that there is a cache information, and as you can see, the server is supposed to send you the PRT, but you don't have access to the server, so the cache information must contain your PRT. So could be really interesting for us.
Thank you, Geoffrey. So now let's talk about the cache data file. So we'll talk about where it's located on the file system, what is like the internal format. So the cache data file is located under the system32 directory. So you will have a bunch of different folders. Then you will have a Cloud API cache, an Azure ID directory, and then you will have a unique H. So this H will change for each Entra ID user who has already logged on the computer. And then you will find a cache folder, and finally the cache data file. So it's the files that we are interested in, and the files that we are going to talk about. So it's admin privileges are needed to read it because it contains encrypted secrets, as well as we can see, we can use this file to do a brute force attacks. So as I just told you, there is one cache folder per Entra ID user. In order to match a cache folder with an Entra ID user, we can use the registry. So under the HKML hive, we can find logon cache folder. Then we'll have GUID and then a name trace ID entry. And basically within this entry, we'll find here each age for each unique user. And then we'll have like different entries, like for each user, we can find the SID of the user, its SAM name, its display name, and so on. So that's all for the file location. So why is it an interesting file? Because we can use this file to retrieve the password and the PIN. So this will imply this will involve during a brute force attack. So if we would like to brute force the password, there is no limitations. However, if we want to brute force the PIN, if there is a TPM on the computer, we will be limited by the TPM. And if we manage to get the PIN or the password, we can use it to obtain the PRT as well as the user GPAPI query key. So it's pretty interesting. So now let's talk a little bit about the previous work what's been made related to the cage data file. So there is one PowerShell script, prtutil.ps. So this script has been released on the AAD internal repository. And basically, it allows to decrypt a PRT file when using a password-based, like when a password is used. However, it does not allow us to decrypt PRT if a PIN was used for the authentication. Also, on the DPAPI lab ng repository, there is a script which was released. It's called ngc-cryptodeck.py. And this script allows to perform some Windows Hello NGC PIN decryption. So as we will see later, there is private key involved. And when we use the PIN, we need to decrypt the private key. And so within this script, there is a lot of stuff that we used for our research. So what was our contribution? So we worked mainly on the cache PRT file decryption when PIN was used. So we released a Python script which can be used to brute force the PIN or the password. And we also worked for increasing the comprehension of the cage data file format. So in order to do that, we had to do some reverse engineering. So we had to target cloudip.dll. So we looked at the authentication process as well as all the interaction with the cage file. So to do that, we had to do some static analysis as well as some dynamic analysis. So for the static analysis, we use IDA on the X-ray decompiler. So it's quite usual for reverse engineers. Something pretty nice is that the PDB file was available for cloudip.dll. So for those who are not really familiar with PDB file, it's simply some debugging files that will include some, for instance, the name of the functions as well as the name of the global variables. So actually, it's quite common for Microsoft to release a PDB file for the built-in DLL. So yeah, when we want to do some reverse engineering, having the name of the function as well as the name of the global variables, it's pretty nice. In addition, we also did some dynamic analysis. So to do that, we created a TTD trace. So TTD means time travel debugging. So we created a trace for the LSASS process using WinDBG. And it's really cool because the same trace can be shared among different users. So for instance, my colleague Théo created the trace, and he sent it to me for analysis. And even if I didn't add the proper entry ID environment, I was still able to work on this trace. And also, each DLL which is inside the trace can be easily extracted for static analysis. So it's pretty cool. Okay, so now let's talk about the cage data file format that we managed to understand. So it's actually quite a simple file format. So it starts with a header. We'll find inside the version number. We'll have a GUID as well. We'll have an integrity checksum for the rest of the file. And we'll have an integer which defines the number of nodes. And then we'll have an array of cage node header. So basically, a catch node header will be used to describe a node. So it will define the type of the node. For instance, is it a node related to PIN authentication, or is it a node related to password authentication? And then we'll have the size of the crypto blob as well as the size of the encrypted blob. So the crypto blob is the blob in green on the schema. So basically, the crypto blob is used to check for the user credentials. And the encrypted blob is the blob which contains the encrypted DP-API equate key as well as the PRT file. So both the DP-API equate key and the PRT are encrypted in a same encryption operation. So let's say, for example, that you can log with PIN and passwords, then you will have two nodes in your cage data file. So we only analyze PIN and password-based authentication, but we know that you can use other means, such as a smart card, for instance. Okay, so a few words about where the parsing of the file occurred. So the function deserialize cloud AP cache is the one who is doing the parsing of the file. So it will populate a structure of type cloud AP cache, and within this structure we'll find pointer to an array structure, and the type of this array structure is tag cage node identifier, so it will contain the node type. As I just told you, there's different types. So one is for password-based authentication, and and 5 is for PIN-based authentication. And then we'll have two pointers, one to the crypto blob and one to the encrypted blob. So the format of the crypto blob will change according to the type of the node. Let's take a look at what the crypto blob looks like when we use PIN-based authentication. So as will Théo explain you in a few slides, when you use PIN-based authentication, it involves some asymmetric cryptography. So you have a private key that needs to be decrypted by using the PIN. So what you will find in the cage data file is the public key, which is associated with this private key. So the public key will be stored in a bcrypt everyday key blob. So this is a publicly documented structure by Microsoft. And then you will find different secrets. So you will find here, you will find an AES key, which is encrypted using the RSA private key. Then you will find a second AES key, but this one is encrypted with AES. And basically, once this key is decrypted, it can be used to decrypt this one. And this one can be used to decrypt, finally, the PRT file as well as the DP-API equate key. So we will talk a bit about that in a few slides. So as I just told you, the format of the crypto blob changed according to the authentication mean. So this is what it looks like when you use password-based authentication. So it's simply a blob of 0x30 bytes, and it's the result of an AES encryption using as an input the derivation of the password using PBKeyDF2, and using as a key the derivation of the equate key also using PBKeyDF2. And it uses a null IV for the encrypt operation. So if you manage to compute the crypto blob, this means that you manage to retrieve the input password. That's why you can do some brute force to retrieve the input password. A few words about the DP-API equate key. So it's stored in a structure named credential key. It's a blob of 0x60 bytes, so it contains a GUID as well as the key, which is stored in a 0x40 byte buffer. And this DP-API equate key will be used to derive another key, like the latest master key. And to do that, we'll use the hmake function. And as an input, we will use the SHA-1 of the equate key, and we'll also use the user SID. So as I just told you, it's stored encrypted in the cage data file. Something interesting to note is that when it's in memory, it's encrypted by the LSA protect memory callback. And so in memory, it's stored encrypted using a symmetric cryptography, and the keys are generated by the LSA initialize protect memory function. So basically in memory, the key will be stored encrypted, and if you reboot, you won't have the same key in memory. Okay, so now I will let my colleague talk you about the cache data file usage for offline authentication.
Okay. Okay, so now let's dig into the process involved for offline authentication. We'll start by explaining how it works when using a password. So Microsoft wants to get rid of it, as it is the less secure method indeed. When a password is used, the PRT is encrypted with an AES key derived from the password. And as Rémi already said, by analyzing the function derived key from secret function from the Cloud API DLL, it just takes the password as an argument to create a key. And this key is created using PBKTF2 HMAC with SHA-256 without a salt, and it's iterating over it 10,000 times as for DP-API encryption. The resulting key, is used in an AES CBC decryption with a null AV again on the cache data encrypted blob. So now we will dig into pin-based authentication. And before that, we need to understand what is NGC. So NGC, or next-gen cryptography, or DP-API-NG, are the same terms for the same, all different terms for the same thing. It provides a set of APIs that can be used to easily encrypt and decrypt content through authorization principles. It works with providers, protectors, and items. And about the provider, it's a component responsible for managing cryptographic operations and interacting with the NGC framework. You have two different types of providers. You have the key storage provider, which will be interest for us for the following slides, and the cryptographic service provider. And about the protector, it's just the method or technique used to encrypt and protect sensitive data. So the NGC folder is located here. You need system privileges to access it. And we'll see that there are some metadata inside to retrieve. And we can retrieve it because it's not encrypted. There is just one file encrypted inside this folder. So here you have an example of the tree command if you use it on an NGC folder. So you have a GUID and a protector and some .dat files. So inside the NGC folder, you'll find the NGC GUID folder, which contains some .dat file. And for example, inside the one.dat file, you'll find the user SID. And in 7.dat, you will find the main provider. So here is the output of a script used using DP-API lab-ng, and it just parses all the different .dat file to retrieve this GUID, the user SID, and other stuff. About the provider, so here we'll talk about the key storage provider, and you'll find, if you use the TPM, the Microsoft Platform Crypto Provider. So here the protector is stored in the TPM chip. And without any TPM, you will find the Microsoft Software Key Storage Provider. And here, the protector is stored locally. That's why we will try to brute force some things here. You can find also other providers, like Smart Card Key Storage Provider, but we didn't dig into this provider. Again, it's the output of some script from the DP-API lab-ng repository. And as you can see here, we have a TPM, and here we don't have any TPM. About the protectors, we will be interested in the 15.dat encrypted data. And you can find also other stuff inside, like the name of the protector, the key GUID of the protector. This key GUID will be missing if it's stored on the TPM. And finally, all the different items, and you'll find the name of the item and the provider name. So for now, we know that what is NGC, and we see how the pin interacts with it. I'm sorry, the brownie pong is not finished yet, as we will have to talk about cryptography again. But remember that our goal here is to decrypt the cache data file by finding the pin. So without any TPM, it's a quite complex process. It first starts with a first RSA private key, which needs to be constructed from an encrypted blob, and this blob is called a bcrypt RSA private key blob. And thanks to this first RSA private key, we'll be able to decrypt the 15.dat file to obtain a decrypt pin, and this decrypt pin will be used to construct a second RSA private key from another crypto blob. All the different crypto blobs are stored inside this folder. And again, even if there is some encrypted data inside, we'll be able to find clear text metadata inside it. So as you can see here, we can find the GUID at the beginning. So the first blob, linked with NGC, is decrypted using DPAPI mechanism after multiple steps, which involves the system master keys, the GUID of the protector, system and security hives, the pin, and some static entropy strings. And after being able to decrypt this bcrypt RSA private key blob, we will be able to construct the first RSA private key, because inside it contains the modulus, the exponent, prime 1 and 2. If you are interested in this process, again, on the blog of TJNet, you will find all the information about the static entropy strings, etc., etc. Then, thanks to this first private key, we are able to decrypt the 15.dat file, which contains 3 different pins of 32 bits. And the decrypt pin, which will be interested for us, is the second one. And we will use the exact same method to decrypt, to obtain a second RSA private key by using first crypto blob key, using the name of the item for Windows Hello for Business, which is this one. And we will be replacing the pin with the decrypt pin. So if we try to sum up all the things that I said just before, we want to decrypt a first crypto blob here. To decrypt this crypto blob, we'll need the pin, the system and security hives, DPAPI master key, and thanks to this blob, we will be able to construct a first RSA private key. Thanks to this first RSA private key, we'll be able to obtain the decrypt pin. And again, for the same process, we'll be using the decrypt pin and another crypto blob to obtain all the information needed to construct a second RSA private key.
Okay, thank you, Theo. So now that we have the second private key, let's try to see how it's used for decrypting the PRT file as well as the DPAPI quad key when using a pin. So we will use this second RSA private key, and we will see that it's used to encrypt an iOS key using RSA. So basically, the result of the RSA encryption is the encrypted iOS key. So it's stored as a blob of 0x100 bytes. Why? Because this is simply the size of a big integer of 2048 bits, which is the result of the RSA encryption using PKCS1.5 padding, because simply when you want to do an encrypt operation with RSA, you need to pad the input with some stuff so that it matches the size of the key. Well, let's go back to our cache data file again. So this is the crypto blob when using a pin. We saw earlier that here we have the public key, which match the RSA private key, and this is the second RSA private key that Théo told us just before. So first, we will do an RSA decrypt operation. We will take an encrypted iOS key, which is encrypted using RSA. We will decrypt it, and we will get a first iOS key. Then we will use this iOS key to decrypt a second iOS key. So to do that, we'll do an iOS CBC decrypt, and we will use a custom IV, which is stored in the cache data file. And the input of this operation is the encrypted iOS key, and it's also stored in the cache data file. So this is these operations. So here we have the AES key, which is decrypted. It was this one before. So now it's decrypted here. So we use it as the key for the AES decrypt operation. Here we have the input, which is an encrypted AES key. For this AES decrypt operation, we will use an IV, which is also stored in the cache data file. And we will get a second AES key, which is now decrypted. So it's almost finished. Now we have this final AES key, and we can use it to decrypt the PRT file as well as the DP-API request key, using also an AES CBC operation decrypt with another custom IV, which is in the cache data file. So there it is. We have our final AES key. We use it in an AES CBC decrypt operation. We'll use another custom IV, which is stored in the cache data file. We'll give as an input to the decrypt operation the encrypted API request key as well as the encrypted PRT blob. And finally, we can get the DP-API request key as well as the PRT file. So this was the part related to PRT and DP-API request key decryption using a pin when there is no TPM. So now let's briefly talk about when there is a TPM. So using a TPM, the format of the cache data crypto blob actually is the same. The main difference will reside about like the RSA private key, the one that Théo told you about. So this time with the TPM, the private key will be stored directly on the TPM, and the pin will be used to access it. So brute force will be really hard. It will be limited because of the TPM. So nowadays there is two main implementation of TPM, TPM 1.2. And with TPM 1.2, the protection is implemented by the manufacturer, so all chips were not equal regarding the mechanism in place. But if there is a TPM 2.0, Windows is able to configure it to lock after 32 authorization failure, and it will forget one authorization failure after 10 minutes. So if you have a TPM, it will be way harder to brute force the pin, and then to get therefore to get the DP-API request key as well as the PRT file. Last word about the TPM. So on a Windows system, you can use the get TPM snippet. It will tell you if there is a TPM, if it's enabled, which manufacturer is it, and so on, is it activated. And you can also use the TPM tool with the get device information, which will give you like the version of the TPM, and that's it. So now let's have a quick demo of the toolset that we released in order to decrypt the PRT as well as the DP-API request key.
Okay, can you hear me? Yeah. So I just created a quick batch script to extract all the information needed. So as you can see here, we extract the cache data file here, then all the NGC folder, the different system and security hives, the crypto keys folder, and also the master keys. I run this script as a system to be able to extract the content of the NGC folder. And then you can see that all the data are here. So I will just extract all the data on my host. And then I just copy the folder here. So here it's done. Okay. So I'll just start by dumping the cache data format file. Okay. I think I have one folder. Oh no, I forgot to unzip the folder, excuse me. extraction in progress. Okay. Up. Again. So here, as you can see, demo effect. We have two different nodes, the one for the password here and the one for the PIN here. So we know that there is no TPM, so we'll be able to brute force the password and the PIN. So we just start by brute forcing the password. I think it will be OK now. So here, so I just specified to the script that I want to brute force the password, the cache data file, and then a dictionary containing the passwords. And here, that you can see that here we were able to brute force the password. So we are able to decrypt the PRT and all its information. And we are also able to obtain the derived credit key. And now for the PIN, it's a bit more complicated. We have to specify all these arguments, the cache data file, a dictionary which contains all the pins, the NGC folder, the master keys, the system and security hives, and the crypto keys for. It starts by printing all the different information about the NGC folder, the different providers, and the items. So as we can see here, this item is related to Windows Hello for Business. And it tries all the different pins here. And then we can see that we were able to find the good pin. And we find the PRT here. And finally, the credit key. The script is available on our GitHub, and of course, PRs are welcome.
Just a little word to finish regarding DP API. First of all, we were just trying to gain access to the PRT because that's what we wanted to do and access Entra ID. Nevertheless, by understanding the format of the cache data file, we found the DP API credit key. So what it is. So just a quick word. I won't give you a lecture about DP API, but DP API is just an API of Windows in order to protect data and unprotect it by encrypting it. The main example that we often use is the Google Chrome password database. So it relies on the master key. The master key is not a key per se, it's just a strong secret. And this strong secret is then used to generate a session key, which is the real key used for the encryption. So the master key was derived from the password users. So for local user, it was derived from the SHA-1 of the password. That's why when we talk about Windows Hello, not the Windows Hello for Business, we saw that we needed the password of the user. In fact, we only needed the SHA-1 of the users, but who knows. Regarding the domain users, it's just derived from the MTH of the users. And for the system environments, they have their own master keys. It's lying on the registries. It's often used for SSID, and it's used for what we saw earlier. So what is this DP API cred key? Because we never saw it in there. Actually, Microsoft wants to get rid of passwords. They implemented Windows Hello for Business in order to have asymmetrical authentication. So the DPI master key, the DPI cred key, does not rely on password. It's just something that is stored on your cache data file and can be decrypted with the PIN. So no, the master key is derived from the cred key by using hashmark SHA-1 of the cred key and the user SID. So I think there is a lot to do now with this cred key, and could be interesting to know where that could lead us. We would like to thank our colleague Laksa. We done a pull request on the tool in order to integrate this new master key type. So in conclusion, what is possible to do with a cache data file? So if the users already used the password on this computer on a full Entra ID environment within the last 14 days, you will be able to brute force the cache data. Of course, it's a PBKDF2 10,000 round with the IS, and we still need to implement it in John the Reaper, but it's a work in progress. So you will be able to do an offline brute force. And after that, you could use the PRT to access the Entra ID with a lot of tools to do that. Broadrecon is one of them. And if you are using a PIN, if your TPM is enabled, sorry to talk to you about it, but from now on, we don't see anything that you can do. We hope someday. But if TPM is not enabled for, I don't know, computers that are not TPM, of course, virtual computers, you will be able to retrieve the PRT, you will be able to retrieve the DP-API cred key. And then after that, the same thing applies since you have the PRT file. So in conclusion, we still have more research to do to understand how it works when you are using other means of authentication. For instance, smart card, if there is another node in the cache data file, do we need to do some crypto crazy like that again? We know that the cache data is really a gold mine. There is a lot of information in there. You will find stuff such as DP-API, PRT, and everything that you want. The bad news here is that TMP enhanced drastically the security for credential, and asymmetrical authentication with the TPM will certainly lead to the end of cache data being a gold mine for penetration tests. So, yeah, we would like to thank a lot of people because a lot of work has been done on everything like that. So there is a few in the room here. We had a lot of reference for our talk. I will let you have a look at our article on the blog post of Synactive if you want to. And we've been a bit quick, but if you have any question, please.
Thanks. First of all, congrats to the mind-blowing research. Like, great. I always wanted to meet the person at Microsoft who designed DP-API and all that crazy shit which you reverse engineered. But now back to my question regarding the DP-API cred key. Have you played a little bit more with it? Because I did some experiments of my own with it, and I came to a conclusion that it is device bound, so each device gets its own cred key, and it's also it also depends on time. So if you ask Entra ID in a month or in 2 months, you get a different cred key on the same computer. And there is a key in Entra ID in an attribute which it used to be searchable device key attribute, but Microsoft moved this data to a different Entra ID attribute. But it used to be there, readable by all users, no longer the case. But my question actually is, have you figured out how Microsoft derives the cred key from the data stored in Entra ID? Yeah, thanks.
So actually, no, I'm sorry. It was really just the burner thing because we were looking at the PRT and we found the creds key here. So we're just trying to understand a little bit what it's used for and why is it here. So no, we didn't had a look further, but yeah, that could be really interesting research to do. Yeah, thank you. Thank you very much.